Fantastic. Without further ado, I'm going to hand you back over to Nick. Thank you, Nick.
Okay. Hope everybody enjoyed the coffee break and the talks this morning. So we have 2 more to go. Our next speaker is Ken Davis from Pennsylvania State University. I've known Ken for too many years now, 20 years, going back to the start of my PhD. I mean, the same is true for all the speakers. I'm very impressed and inspired by the breadth of work that Ken and others do, and I'm very excited that he was able to make time for this workshop this week. And he's going to provide some more perspective on trying to quantify emissions with greenhouse gas observations and models. And I think we need to bring the slide up, this presentation up.
Right. And I advance from here. Cool.
Yeah, I met Nick when we were both grad students together. No, that's a joke. Sadly, not sadly. Anyway, on we go. So I'm going to talk about work down a little more in the weeds than what you heard about earlier today, but connected. I tend to work on the ground a lot, but it has relevance to atmospheric measurements. And I'm going to really try to address the charge, which is what kind of measurements would we need to advance this field. And just to hit this again, we know global greenhouse gas budgets not because of adding up inventories, and Anna already got to this point, but we know it from the atmosphere. And so here's, one of I use this in my classes a bunch. This is old now. It's the AR5 version of the global carbon cycle. You see all these sources and sinks that add up to that total in the atmosphere rate of increase. And we don't know that rate of increase in the atmosphere by adding up all the sources and sinks because their uncertainties are too big. We know that because we make measurements in the atmosphere. And the slope of that line tells us what that number should be in that figure. And so the atmospheric data are really critical. Similarly for methane, this is a little out of date now too. This is a global methane budget from the Global Carbon Project, and you see the uncertainty bounds and the methane accumulation rate in the atmosphere is not very big, but the uncertainty in all the individual sources is quite large. The newer version has smaller bounds on those, but you still don't get that answer by adding up all the sources and sinks. You get that answer from this curve. It's a little different with methane because in this case, it's not the slope, it's the concentration that tells you the source balanced with the sink, but it's still the atmosphere that tells you the answer. So the atmospheric measurements are really critical. And so we call this top-down, just to set terminology, top-down. Atmosphere tells us what's going on. The atmosphere sees everything. And so that's very handy, but the problem is it doesn't tell us why. It doesn't tell us what's happening, what the process is that's causing the flux. So we need these bottom-up approaches too to complement the top-down. For example, if you look at that methane curve, you see that the methane rate of increase stopped, then it increased again, and we can't explain it. We see it from the atmosphere, but we don't know why. So we need the process-based understanding to explain why. And so we need things like models of people. I could point with this right now, maybe not. Yeah, I can. We need things like, no, it doesn't work. I'll point with this. We need models of people and animals and ecosystems to understand what's going on. Machine learning is great, but in the end, we have to understand the process or we can't work on mitigation. We need to know the causes to mitigate emissions. And without these complementary methods, we can't do this management. But we can't go from process to the planet. That's too big a jump. For example, if I decided to go off and understand cows. I don't have my picture of burping cows, I'm sorry. But if we decided to do a really great study of cows in Iowa, it'd be wonderful information, but it wouldn't explain this curve, right? We'd need more to put together. So I argue that we need something in between. And I think that our community has begun to converge on this kind of a multi-scale approach. So I'm going to sketch out what this multi-scale approach is, and then I'm going to tell you what I think we need to make it happen, at least some of the parts. So first, we do need this process-based understanding. We need the bottom-up models. They're very important. They need data. And so imagine a field of widgets that emit or remove. People have a harder time with sinks, but Imagine a field of widgets that exchange greenhouse gases, and one example might be leaking valves in an oil and gas field. It could be an ecosystem model, and then it's a lot more complicated, at least in terms of the modeling we apply. Or it could be really complicated, like a city where we've got the widgets that emit and the plants growing together. But in any case, we need observations to drive that process model. So that's one part of the system. The part that we haven't heard yet about, which I think is really important, I've got two parts that we haven't necessarily heard about, is local scale flux measurements. Flux measurements where we watch a bunch of the widgets at a scale where we can go and test our process model and improve it over time. I think of this as things like eddy covariance flux measurements, which Derek mentioned, and plume measurements, which some of you have worked on. That's to test the models. And so this is my new emoji that's called What the Flux. It's a cartoon of a eddy covariance flux tower, and I'm not going to go into that because I don't think we can use this too much, and it'll measure fluxes upwind. Or we could measure plumes if they're point sources. So area sources, eddy covariance is good. Plume measurements are good for point sources. We need those. The area we sense is like kilometers squared type areas. We need that to test and improve the process models. We're not going to cover the whole planet with those things. That's not practical. And then we need to measure the atmosphere for this sort of an inversion approach, but I would argue that a regional scale is really critical to bridge between important geopolitical, ecological units and the planet. Can't just go straight to the planet. We need to go to the planet, but we need something in between. So this stolen and adapted from Scott Denning from years ago, who was actually Nick's advisor, who is my colleague. Yeah, anyway, I'm older than Nick. You measure upwind, you measure downwind, the air blows across this whole domain. We measure the change in concentration, and based on how big the box is and how fast the air is moving, we can figure out what the sources or sinks are in between. That's an inversion. Those together help us to understand the system. This is the system that we have to build. If you read the US Greenhouse Gas Measurement Monitoring and Information Strategy, it largely says this. Not exactly, but something like this. So I think we're kind of saying, yeah, all right, this is a way forward. We got to do this. And this is the same words. If we pull this off, then we can iterate, improve, monitor. And if this really works, then we can mitigate with confidence because we know where the emissions are coming from. We know the cause. We verify if they're actually changing. That's where we got to go. And the measurements, yeah, they could be in situ, they could be remote, they could be mobile, they could be stationary, they could be ground-based, they could be space-based, they could be airborne. Yes, probably need all of the above. Pause. All right, we need to set some vocabulary. And you all know this anyway, like Anna said. Come on, where's the folks in the room who don't really know? But just in case, what's the boundary layer? I'm talking about the atmospheric boundary layer a lot, so I brought a little snippet of what's the boundary layer. So this was a nice day when flying over, maybe this was Ohio, in a C-130, taking pictures out the window. There was a nice, polite cloud deck, not a troublesome cloud deck that just sat at the top of the boundary layer and said, look, that's the boundary layer, that layer of air. That's the box of air I work with a lot. I was really sad when Derek said we can't measure this from space. It's really bad. And it's turbulent. There's a lot of mixing going on, and I care about it because if you have greenhouse gas exchange, where does it show up? In the boundary layer, right? So we really need data there. So that's the box of air. It's turbulent, emissions get mixed into it, and then it gets carried along by the main wind. Here's another day with some patchy clouds. You can still see that there's some layer of air below those patchy clouds. Here's a day where there are not many clouds, and here's a day where there's no clouds. So you can say, is there still a boundary layer? Well, yeah, there is. How can we tell? And here's a measurement of the sort that Derek has shown us. This is older than when I knew Nick, or maybe close. This is from 1994 from an airborne LiDAR, not a space-based LiDAR. But there's an aircraft that was flying up here, trust me, shooting a laser, looking at the reflection, and you see this bumpy high reflectivity zone. That's the convective boundary layer. So you can see it even if there's no clouds. This is a cloud-free day. If you look from the ground with a Doppler LiDAR, Derek talked about Doppler LiDAR, you'll see that bumpy area, the warm colors are strong vertical motions, are where there's turbulent mixing happening. It's another clear day, but there's a lot of turbulence, and you see the turbulence shuts off above. If you look at night, it's really quiet. It's because there's not much turbulence at night. The sun isn't heating the ground. So there is a boundary layer out there. And just in case you've heard that hot air rises, well, kind of. You know potential temperature, right? If it's potential temperature, that's true. And so the boundary layer is cold. Temperature versus altitude. There's often a strong capping inversion. It means this stuff is really stable. It doesn't want to go up there, which makes my life easier in some cases. And so that box of air, the boundary layer, is what we work with a lot. Okay, there is a menace out there. These damn things. And Derek brought this up too. When these things show up, they punch holes in that beautiful boundary layer and make the world a lot more complicated. Anyway. All right, so there's the aside. Now back to the kind of the main show. What do we need to do to pull off that observing system, in my opinion? This thing. So this is just a list. I'm going to highlight pieces of the list and tell you things about it as we go along. So rather than read the list, let me just hit it a piece at a time. One thing I think we need is regional scale atmospheric greenhouse gas concentration data. It's very, very helpful. I'll show you examples from 2 test beds. I'll tell you about stuff that my group does because I think it's fun and it's illustrative. We've been studying Indianapolis for reasons that are not worth explaining for more than a decade. And this mishmash of all the different measurement systems and universities and such gives you some idea what's going on. All these funny colored diamonds are places where we measured concentrations. We measure them in the boundary layer from towers because it's easy and the signals are big. Doesn't mean we don't want to try to do this with other platforms, but this is a test bed, a place to prove methodology. And so we instrument communications towers with Picaro cavity ring down spectrometers at a whole bunch of places. We can then measure the enhancements in concentration over the city as a function compared to what's upwind. And we can use that concentration enhancement to infer the sources and sinks, in this case sources, anthropogenic emissions. And we compare that to a model where we put in what we think the sources and sinks are. To the extent that they agree or disagree, we adjust the sources and sinks to come up with what we hope is the truth. That's an inversion. In this example, we're using this state-of-the-art fossil fuel emissions inventory from Northern Arizona University, from Kevin Gurney's group, HESTA. And we've got it divided here into the traffic and the stationary fossil fuel sources, and you can't even tell the difference between the inversion and the model. These things agree really, really well in this heavily instrumented, state-of-the-art research test bed. And on an annual scale, we're down to like plus or minus 3%. This is killer. This is great. We nail it. So we can do this. This can be done. Test bed, Permian Basin. You've heard a lot about Permian Basin from satellite. We do the Permian Basin from towers. Both work. And again, communications towers with cavity ring down spectrometers surround the basin. The purple things are wells. These are enhancements. You can see there's high concentrations when the wind is coming from the wells to the towers. We then use a transport model to tell you where any measurement came from, upwind, and conduct an inversion, and we can get emissions versus time. This is over years. We're doing this every day, continuously, which is really cool. We can get monthly fluxes to about plus or minus 20%, and very different from the picture in Indianapolis. We are roughly 3.5 times larger than the inventory that the EPA produces. So in this case, the inventory sucks, to be honest. It's terrible. But we know this. We know it's terrible because we have these measurements. So this is really important to have the atmospheric evaluation of the process models, or else how would we know? So obviously regional greenhouse gas data is great. It helps us, but we can't build test beds anywhere. If we can do everywhere, if we could do this more from space and cover the planet, lovely, be fantastic. This also illustrates one other need. In this case, I can tell you, I throw pie in the face of the EPA inventory, but I can't explain what's wrong with it. That's not so helpful, right? If I can't explain what's wrong with it, how do we make it better? So that's a serious criticism we've received, and it's a good criticism. We need to get at why. And so we need these process scale local flux measurements to understand what's up. And for plumes of methane, this can be done. If you drive downwind of a gas well and it's leaking, you could see a peak in concentration. Or some of you all out here have done this sort of work where you can see the plumes from either aircraft or from satellite. You can see these plumes coming from the point sources, and that's a really great local scale flux measurement that can help us to understand what's going on if we also have the information at the ground about the processes responsible. We're building that information to make this work better. Okay, pause. How am I doing? Not bad. So that's greenhouse gas part, but we're talking about greenhouse gases and winds. So I'm going to move now into the meteorological portion of what I think we need. And I made some bad guesses, and you'll see why. So we need regional scale atmospheric transport data in order to do these regional scale inversions. I think I break this up into 3 scales, turbulent scales. Small regions and large regions. And if you were one of my students and you came into me and said it's small, I'd say, oh, come on, what's that mean? So I'm going to tell you what's small, what's large in my opinion. I'm going to start though with the turbulent scales, going back to this plume measurement. So these plume measurements, we need a dispersion model to explain what's going on. And I'm going back to coffee because I like the coffee analogy. I do this with the boundary layer a lot. You drop cream in coffee, you stir it. After it's gone around a couple times, it's all just tan. Same thing with the boundary layer. It is turbulent. There's a mean wind. There's a certain mixing depth, about 1 kilometer ballpark. If I've got something emitting, it's going to go weep-a-deep-a-deep up and down and get mixed. And if I then say, imagine 100 of those particle trajectories, close to the source, it's bunched together. By the time you get downwind, it's all mixed up and it's just tan. And so this distance, hundreds of meters is where we usually do this sort of plume work or eddy covariance work, maybe down to a couple kilometers. By the time you get out to like 10 kilometers, it's well mixed in the boundary layer. We don't do the plume work so much or the eddy covariance work. So this is the range for those process-based turbulence measurements in space. I don't know if remote sensing can help us with that. With the greenhouse gases, yes. With the meteorology, I don't know. I wouldn't be so optimistic. Maybe. Same question. Can we help? We need winds for this sort of thing. Can we get winds from space that would be useful? Don't know. Eddy covariance is a lovely technology. It's great for area source flux measurements. I don't think we're going to be doing this from space anytime soon. But I'll go really fast since this isn't entirely relevant. We do this from towers. Like this is over the city in Indianapolis. You can measure a few hundred meters downwind every half hour continuously and compare to things like a 200 meter resolution fossil emissions inventory. You can see lovely things like cold and warm season, time of day, CO2 flux, flux versus direction. When you look at the highway, there's high emissions. When you look at the non-highway, you see even photosynthesis in the summer. We can then decompose this into bio and anthro using CO and CO2. And then we can compare the fossil part to this emissions model, Hestia, and it's stunningly good. It's remarkably encouraging. We can do this in some places. We even picked out the COVID lockdown change from one of these, and the model and the measurements both seem to nail it. So that's encouraging. Now the harder stuff. Regional. What's a small region? A city is a small region. A gas basin is a small region. Why are they small? I was happy to hear Derek talk about boundary layer, free troposphere exchange. I would say it's small when the air often flows across the region without one of those damn clouds messing up my boundary layer, right? So when the boundary layer stays as a unit, I'd say that's a small region, on average. As a thunderstorm comes through, I'll just throw out the day. I don't need it. I don't need every day. I just need a bunch of days. This is a picture from the book I still use to teach boundary layer meteorology, Stull, 1988. This is the high pressure system, low pressure system, convergence, lifting, weather. Weather is what messes up the boundary layer, causes vertical motion. This is yesterday's weather map. It's a lovely day yesterday in like Iowa or Illinois, right? High pressure, it's got to be nice and sunny and cool, winds from Canada. How long is it going to last that? How long is that going to last? Like 2 or 3 days, right? And then the next front's going to come through. So a few days is the division between small and large. If I take a day and multiply by a typical boundary layer wind speed, you get 400 or 500 kilometers. So smaller than 400 or 500 kilometers is small. Bigger than that, it's large. I have to worry about this exchange with the deeper atmosphere. So that's bigger than a city or a gas basin, but it's smaller than the Corn Belt, and it's sure smaller than the Amazon. So for those larger scale units, which are important, we need to worry about the vertical transport. Okay, in the boundary layer, still doing okay? Still doing okay. All right, in the boundary layer, then, if it's the small region, my box of air can essentially be the boundary layer, and I can forget the vertical exchange. So it's how big is my box? We do pretty well simulating boundary layer depth and boundary layer winds and wind speed. Not great, but not bad with models. If we have data that we have to constrain the models in the area, if it's a less data-rich region, it might not be so good. Even in those cases, we should evaluate and improve the models because we could do better, and we should work on uncertainty assessments in those models if we can. Ensembles are one way to do this. I'm just going to pitch a bit of an ensemble message here. You heard about Raywin-Sans? We used a bunch of Raywin-Sans in the upper Midwest to compare to a weather model that we ran. Not one weather model, but 45 versions of the weather model. Don't worry about this. It's just a whole bunch of members of an ensemble of the weather model. And we compared and computed errors in wind speed, wind direction, boundary layer depth. And that's nice, but is this a representative uncertainty? Not necessarily. These are just 45 random members that I grabbed off the shelf. It doesn't mean they are representative of uncertainty in our model. So instead, we compare those measurements in red to the model envelope in blue and make a rank histogram. You say, all right, here's all the different models, 1 through 45. Where did the measurement fall? Now where did the measurement fall the next time? Where did the measurement fall the next time? And you make a bar graph of that. And with this example, at least, you find out that most of the time, most of the models, the wind is too high and the boundary layer is too deep. I'd like this to be flat. This is too narrow an ensemble that all the model members are on one side of the measurement instead of the measurement being jumping back and forth within the members. So this is not a good representation of model uncertainty. This would be underestimating model uncertainty. So what we can do is throw out a bunch of members that all look the same and try to flatten this out. Flat rank histogram, then you got a model that you say, this is a better measure of uncertainty, and you can check the bias. If the bias is small and the spread is good, you have a useful ensemble. So we went to town with this with ACT America, this NASA Earth Venture project, and we made flux ensembles, boundary ensembles, transport ensembles, then made modeled CO2 ensembles. It hasn't really gone very far, to be honest, but we've worked on building these systems. Okay, so that's small regions. More abundant measurements of boundary layer winds and depth would be very helpful. I was more optimistic that we could do this from space, but Derek was not so cheery on that message. Anyway, on we go. Big regions. Corn Belt, southeastern forest, the Amazon. The box is going to be more complicated. The box includes vertical mixing with the rest of the troposphere. So we've got to deal with that problem. Fronts, low pressure centers, convective clouds. That's what's going to cause this vertical motion. This is not just horizontal wind. This is vertical transport as well. We tried to go at this with this ACT flight campaign. We put in 1,000 hours flying across fronts all over the central and eastern U.S. And we specifically went for fair weather, the fronts, and then the fair weather that followed, trying to get at the synoptic sequence. We measured, so here's an example. This is pre-front in Iowa, and you can see the air is coming from the south. This is across the front. Air is coming from the north and the south, and this is post-front, where they got the cold air coming in from the north. Just to get that sequence of events, measured everything we could stick on the aircraft. We measured the impacts on greenhouse gases. We measured the winds. We measured the boundary layer depth, but we couldn't measure things directly like the cloud lifting or the mean vertical velocity. That's just not something we have hardware to do readily. But you could infer it. I heard discussion earlier about could we back it out from the other things? Yes, possibly. With greenhouse gases, though, you never know, is it the transport or is it the flux that's causing the problem? So those two things are confounding. And honestly, this data set has been largely avoided by most of the folks doing global inversions because they say fronts, weather, don't want to do that. But I think we have to. So can we improve quantification of these processes using space-based measurements? I hope so. I think this would be wonderful progress to put in combination with new greenhouse gas remote sensing. And we could build this system better. That's it. Thank you very much.